unless you're doing definite integral substitution. Then it kind of sucks.
You lost me there.
Yeah.
So why is I don't know, because it's something in the file creation, because when I don't create the files it takes like 1 millisecond or 0.1 mil, or like, you know, it takes the amount of time it should take, but as soon as I add in this sprintf and the save JPEG, it takes 2 hours and 22 minutes.
I don't know, that's strange.
Yeah. Yeah, so I don't know. Like, I was looking at it, and as far as I can tell, I have the syntax right, but something about those two is adding 2 hours and 20 minutes.
So you are using defined values for the beginning and the end, right? You're not making it loop to find the values.
How so?
Well, when you save it, you need to give it a beginning point and an end point of what to save in the array.
Yeah, start and length, right?
Yeah, that would work. Okay, I just want to make sure that that's right, because that could cause a problem where it's just looping through it over and over and over and over trying to find where it's at. But
yeah, and judging by the fact that they're about the right size, I'm guessing my length is doing it correctly.
Yeah. That's interesting.
Yeah, like if I just comment out my 2 file saves right now, that's change directory, 5 claim time, it takes 0.128 seconds. But it takes way longer than that if those aren't commented out. Alright, let's see.
So
the first,
your sprintf should be inside of the for loop, inside of the if statement, inside of the very first if statement.
Oh, yeah, maybe that will help. Well,
so you should have your first if statement should be if data I equals 255.
Yeah,
data I, right?
Yeah, that's what. Yeah, and then I have that. I set my start. I iterate my count.
And then you have another if statement.
Well, then I have the second for.
Yeah, and another if statement in there to find the beginning of the next one, and then a third loop to go backwards. But inside that first if statement,
that's what I should have. So I shouldn't have it. I should have it inside that, not just at the end of the for.
Right. Because that is, once it finds that spot and then does everything else, it has the beginning of the second one and the end of the first one, and then it should create. So all of your computations should be after it finds all that stuff, but inside of that if loop.
Well, the save JPEG call should still be at the end of the first for, right?
No,
that should also be in the
it should be in the if. It should all be in the if, because once it finds that first one, then it's going to go through the rest of that garbage, and then it's going to come back and save it, and then it's going to start the loop again and find the next one.
So you're saying so it should be like in the very inner loop is where I should calculate the length and sending it into save JPEG?
No,
brain.
No, so you have the first for loop that starts at the beginning of the file.
Then it looks for the start,
and it finds the first set of characters. And then once it finds the first set of characters, then you go into the second for loop, and then the third for loop, and then you break out of both of those.
Yep.
But before you leave, before you start that loop, the first loop again, that's where you need to save it.
Okay, so
it should be right after the breakout of the second for loop.
Okay, so that would be in my. Wait, do I have that break in a wrong spot? Where's my 4
Good morning,
break?
everyone.
If
Good morning. How are you?
Man,
Splitting
have I
you guys
had
for
a
a couple
day
minutes.
yesterday trying to do CSI.
Yeah, I've finally been actually getting on this one. You know, I've been behind for a while, and I did a good chunk to catch up, and then I hit CSI and I got stuck again. But now I'm working on this one. It's working. It's grabbing all 29 images. It's taking 2 hours and 22 minutes to do it.
Oh,
So which Terry's trying to help me figure out where is causing it to take 2 hours and 22 minutes. It's something about where I have my file saves, because without them it takes 0.128 seconds.
Yeah, mine, I had it always counting the images. I had all 29, but I just couldn't save them correctly, and now some of them have parts of the correct images, and I just had to move on for now. So I'm like, that's at least much better than I had it. So
My images all seem to be saving correctly. Because I think I'm getting, you know, it's hard because some of the images are cropped, so it's hard to tell. I think they're all the right images.
yeah. Some of them are cropped in real close. But
Yeah.
As long as when it opens up your viewer window, as long as it doesn't stop like halfway through, then you should be good.
Yeah, that one was a very fun one. I think it was fun.
I think that's a record.
2 hours and 22 minutes.
I know.
But it's doing it's, as far as I can tell, it's doing it correctly. It's just taking for goddamn ever.
Yeah, that's funny.
I wonder what you could be doing that would take that long.
Well,
Well, Terry's just
the save was outside of where it was supposed to be, so I think it's just like doing a whole bunch of loops.
yeah. My save was in my save was so far in like my initial for loop. After all
like
the ifs and
Maybe
fors.
every time it moved 1 byte forward, it would save it, and 1 byte forward would save it.
That's the theory right now. So he's saying I should have it after the second for loop before the break.
No.
After
It should be inside of the first if statement after you find everything else.
Okay, yeah, okay. So wait, where's that bracket?
That way
You
it
show me your
only-
bracket.
It only saves it if it finds that first set of characters.
Oh, damn it.
Otherwise, it's doing it every single time.
Where's my notepad? Where's my
And there's like 15 million bytes in that or something. How big it's like 15 million, right?
Yeah.
It's huge. So that means it was saving 15 million times.
That might explain a difference in time.
Yeah, and that's why it wouldn't iterate your count, and it would only show the 29 photos because it's just saving it over and over and over and over and over. So count 0 has been saved 15 million times. Which is fun, right?
Okay, so inside the first if
15
loops
million
at
minus
the very
29.
end, so it finds the start, it goes through, it finds the end. I need to move my length in there as well.
That's funny. That's pretty awesome, though.
Well, yeah, I was saying they're going to, I'm pretty sure that when I talked to people about this, they weren't saying they had to sit there for 2.5 hours waiting for it to finish running.
Right.
No.
But I was also just happy enough. But like last night, I was running it the last time after I ended up. The way I ended up doing it was, I have my counting one for name purposes, and then to find the end of the last image, as soon as count hits 29, so it's looking for the 29th image, it starts at the end of the array and comes backwards looking just for the end, instead of like going forwards and looking for the next start and then the end. So once I put that in, it finally correctly grabbed the 29th image, and I was happy.
It just
But then it was still
2.5
taking,
hours.
yeah, still taking 2.5 hours.
Well, moving that save spot will fix that.
Let's see. Oh, I should have just commented them out below just in case, but I think I did. So,
Well, how are the rest of you doing?
Great.
Yeah. I still haven't
Doing
gotten around to
good.
posting that schedule for the Zoom thing and putting the last kind of like little reflection assignment up yet. Let's see what happened. My daughter's car broke down yesterday while she was
Oh no.
up in Auburn.
Oh, that's a bummer.
Apparently, when she started it up, the engine started shaking violently.
Uh-oh. Was it a broken motor mount?
Well, don't know.
Is it it might be a bad ignition coil.
Who knows?
Oh, God, that was so much faster.
Who knows? We did find a little puddle of oil on the ground where she normally parks in front of the house.
Yeah.
And apparently when they checked the oil, it was pretty low. So it might have, for some reason, just dumped all its oil.
Yeah, that's not good.
You know, or it could be a motor mount, or who knows. So it's in the shop now. But, yeah, that was like.
Hopefully it's not too serious.
I hope
Yeah, that's a bummer. That's scary for her too.
Yeah.
No fun.
Yeah, that's not good. I have to be careful driving on windy days for fear of my hood managing to tear off my bumper, which it is strapped to, because my hood will wiggle. And I'll be driving down, and all of a sudden I'll see it bump up higher than usual. I'm like, oh, I need to slow down. That's too much weight. Yeah, moving those saves. I ran it. It finished in 0.103 seconds. I have 29 images, and they all seem to be images.
Yay.
Good.
So yeah, moving the saves, that was it. It was literally just sitting there saving a few million times.
That's awesome.
But there we go. That's another one done.
Yay.
Hey!
All right, so I thought I would spend today doing like, well, so some of you have already been through this quantum computing stuff in another class.
Yes.
Right?
I will
But
gladly go through it again.
but this time we'll do it in C. So I have this like video to show you. Now, the people who are watching on YouTube, it's going to, I'm just going to like blank it out, because the problem is that YouTube's content ID will see that I'm showing somebody else's YouTube video within my YouTube video, and they will cut it. I don't want, you know, yet another copyright violation on my record. So what
Yeah,
I'm going to do
those are
for the
annoying.
YouTube people is I'm going to post in the chat the name of the video that I'm going to show, and then you all can go and maybe watch that video while I blank the screen out, and then come back when that one is done. So let's see, what is the name of that video here? I did this on, what was it, Monday in my other class, and then halfway through the video, the YouTube people were like, it blanked out. It said video is blocked. And then sure enough, it was blocked. So let's see.
A good feeling of turning in the code.
I know, I got really familiar with all the Bitbucket stuff over the past couple weeks.
Well, luckily the recover one is not a bit bucket. This one I can just download and turn in.
That was my final project in 50, was creating it automatically pushes files to Bitbucket. Saves
Alright.
everything and keeps it all local.
All right, I just put in the YouTube chat the name of the video that we're going to watch. So I don't know if you can pause the live stream and then go watch that, and then come back when that one is done. And then I will show the people who are on Zoom, I'll show the video because Zoom won't cut it out.
Oh man, if you guys haven't seen this, you are in for a treat. If you're a nerd like me.
All right, so I'm
It's
going
a very
to
cool
I'm going to
video.
blank the YouTube video stream, and they won't see anything for a little while. They'll just see a screen that says "We'll be right back," and then when we come back, then we'll be done. I know it is, huh? What did you? What's the best part of that?
The teleportation.
Huh?
After watching the two slit,
Mm-hmm.
it's like, I don't know, it's so real. It's absolutely possible. The idea that you could send data nearly instantaneously with no physical link. It just goes into, I don't know, subspace, I guess, and ends up at the other spot. I
Yeah.
mean, think you do it, you go to Mars. You could send data from here to Mars instantly, right? At the speed of light. That's
So
amazing.
what you're talking about there is this has actually been shown in the lab to work, that you can take two quantum particles and you can entangle them, which means they are now tied to each other. An effect on one will affect the other, and this is not normally seen in the real world. Like, if I bonk this person on the head, it doesn't cause this other person to feel it or anything like that. But you can take these two particles and you can entangle them, and then you can take one of them and launch it into space. And then you can affect the one that's still on Earth, and the one in space will be affected.
Yeah, it's pretty.
That's pretty cool. And you didn't like send a signal from the Earth station to the satellite. You just, bonked it over here, and the other one felt it.
Hmm.
And
Yeah, it's so cool.
So that's pretty cool. And like I said, that's been actually shown to work. It's not science fiction anymore. And so that does have some implications in being able to maybe send messages across vast distances without consuming all the energy needed to make a big giant radio dish and receivers and antennas. All you have to do is just entangle the bits, send one of them into, on your satellite or wherever, and then you could basically like send ones and zeros by just flipping the qubit over here, the quantum bit over here, and have the other one flip as well. Now, there's
Pretty
still,
cool.
apparently it's still speed of light, right? You can't just instantaneously transmit it, but you could do it without consuming all that energy of sending a radio signal up to it.
Hmm.
Let's see. So hopefully people who watched the video are back now. So just a little review here. In a classical computing, you've got a classical bit, and it's always either a 1 or a 0. It's never like both. It's never neither. It's always either a 1 or a 0. We can tell for sure that it's a 1 or 0. If you flip a coin, even if you don't look at the coin, you know that it's going to be either heads or tails. And it's not going to just spontaneously flip to the other one. And then as soon as you look at the coin, then you see what it is. But it's not going to change while you're not looking at it. A quantum bit, by contrast, uses a particle with quantum properties. These could be things like photons, they could be electrons, they could be an atom with energy states. For example, here's kind of this naive high school view of an atom, but it works well enough for us. You've got this nucleus in the middle, and then you've got an electron that's orbiting, if you will, around the nucleus. And that electron could either be in a high energy state, in which it occupies an outer orbit, or it could lower itself down to an inner or lower energy state, in which it occupies a closer orbit. And the cool thing about electrons and their orbits is that they don't, like as they're orbiting around, they don't gradually move down into the lower orbit, and they don't gradually move out of the lower orbit into the outer orbit. They just seem to snap from one to the other instantaneously without occupying the space in between. Scientists have basically photographed atoms, and they can see there's like this gap in between these two orbits, and there are no atoms ever in that gap, or no electrons in that gap. They're always either in the inner orbit or the outer orbit, but never in between. And so that means that you can use something like an electron to represent a 0 or a 1, and it's never in between, but you don't know whether it's in that inner orbit or outer orbit unless you actually look at it.
Yeah, it's so wild.
So that's called superposition, in which it could be either or both, or actually it can't be both, but what superposition really is a probability, that the electron has a probability of being in the inner orbit or in the outer orbit. You can calculate those probabilities, but you don't know for sure where it actually is until you look at it. And that's the strange thing about quantum mechanics is there's this, you heard about the Heisenberg uncertainty principle, in which you don't know about the state of something, a quantum thing, until you actually look at it. Until then, it seems to exist in this nebulous, well, it could be one or the other, but we don't know. It is almost like a coin flip. You know, while that coin is flipping in the air, you don't know whether it's going to be heads or tails, and even when you cover it up, you still don't know, but when you look at it, you do know. But a coin isn't a quantum particle, because it doesn't instantaneously go from heads to tails. It rotates in between the two of them as it goes around. So here's that game that was shown in the video. You start with a quantum bit in the 0 state. This is the way you represent quantum bits. You use this vertical bar, and then a number, and then a little greater than sign. And then here's that first coin flip that the computer does. This is called the Hadamard operation. And then there's an X operation there, where you can either flip the coin over to its other side or not. And then there's another Hadamard operation right there. That's the other computer's flip. And then the projection is that when you do this, it ends up being back at 0 again. So I thought we would start out writing a C program that simulates the game in a classical sense. Not using quantum, just regular coin flips. So we're going to play that game having the computer flip the coins. This is pretty easy to simulate. So I'm going to start with a couple of defines here. I'm going to make heads be 0 and tails be 1. And I'm also going to define games to be 10,000. That'll be the number of coin flips we're going to do. We're going to do 10,000 coin flips. So the first thing we do is initialize our random number generator. And we're also going to keep track of the number of times the coin ended up being heads. So the number of times the computer won. Then we're going to run a loop. That's just going to flip the coin 10,000 times. And so inside this loop, we're going to initialize a coin to be heads. And now it goes through, now the computer plays. So the computer can either flip the coin or not. So there's a random choice to either decide to flip the coin or not. And then if the computer does decide to flip the coin, whether it comes up heads or tails is itself random. So there's actually two random things happening here. First is a decision whether or not to flip the coin. And the second is the outcome of the flip itself. So what we'll do is we'll call the random number generator, which is going to give us a large integer. And then if we do mod 2 on that integer, we'll get either a 0 or a 1. And that'll tell us whether or not we flip the coin. Okay? So if random mod 2, so if it decides to flip the coin, set the coin to be a random value, either heads or tails. So that's the computer's choice. Now the human can either decide to flip the coin or not. So it's kind of the same operation there. And then finally the computer can decide whether to flip the coin or not. Okay, so now that we've potentially flipped the coin 3 times, we're now going to see, did it come up heads or tails? So if the coin is equal to heads, then increment our heads counter. Okay, and so that's the whole game. We're going to do that 10,000 times. And then we'll just end by printing out how many times it came up heads. And here we go. So out of 10,000 games, 10,000 flips, it came up heads 5,694 times. We can do it again. It's about the same. So one thing you might be asking at this point is, why isn't it coming up 50-50? Why is it always slightly more than 50%? Do you know why? So no matter how many times you play this game, it's always going to be slightly more than 50%. We could even increase this to 1,000,000. It still comes out to be about 56% of the time it comes up heads. So the reason for this is because the outcome of the coin flip is not totally random. It starts out being heads. And there is a small chance that the coin will never be flipped. Remember, the computer can either decide to flip the coin or not. And then the human can decide to flip the coin or not. And then the computer can decide to flip the coin or not. And if in all 3 cases the computer decides not to flip, and the human decides not to flip, and the computer decides not to flip, then the coin will come out heads. Because it started out heads.
Yeah, when you change the int heads, or when you change the coin to tails, it flips it. So it ends up being about 44%.
Right. So there is a small possibility that the coin will never be flipped. In which case, it'll come out to be heads. So heads has a slight advantage in this game because there's a chance it will never be touched. And that's why you end up with about 56% of the time it comes out heads. So the computer has a slight edge on this game, just a slight edge. It's not 50-50 like you'd think, but it's still pretty close to 50-50. Okay, so that's how we could simulate the coin flip game in a computer program. And we can see, you know, it's well, close enough to 50-50. And you probably saw in the video, she kind of glossed over the fact that the computer won actually 56% of the time. But now we can run this program on a quantum computer. IBM makes their quantum computers available for people to use. All you have to do is sign up for an account, and you can use one of their 8 or so quantum computers. And so I've done that here. So we're going to create so the way you program a quantum computer today is kind of like the way that regular computers were programmed back in the 1940s and 1950s. You had these big, giant computers that filled up entire rooms. They had to be cooled down. In this case, quantum computers have to be cooled down to near absolute zero. Otherwise, you have these quantum particles just randomly changing states. But if you cool them way down to near absolute zero, then you can control better whether they're in a 1 or a 0 state or in superposition. So that's the big problem with this, is you have to cool them way down. And even if they have any temperature that's slightly above absolute zero, you know, you can't get it down to absolute zero. So any temperature slightly above absolute zero means it's going to introduce a little bit of error in the readings. So with a typical quantum computer, you can't just run the program once and get a result. You have to run it like 1,000 times and then average the results. So we're going to program this computer by dragging and dropping in the various operations. And the only two that we need to play this game are this H operation and this is the not operation. The not is, you're going to flip the coin or not. So we only need one quantum qubit, or one qubit, to do this. So I'm going to delete the other two. And I'm just going to drag in H, and then the not, and then an H. And then we're going to measure what we got. So this would be the case where the computer either flips the coin or not. That's what the H does. It stirs that mixture of paint where it's either heads or tail. It stirs it up. Those two different colors get stirred up. And then in this case, we're going to elect to flip the coin. So we're going to flip it to the other side. And then we're going to stir the paint can again and then measure to see what we got out. And we can actually run this. Well, first, let's save this. Let's save this as coin game. And then we're going to run it. Now, we can run it on this particular quantum computer. It has only one qubit that you can use, but there's 12 people ahead of us in line. Let's see, what do we got here? There's 13 people. Oh, maybe we can do this one. This one here has 5 qubits. 17 jobs, 25 jobs, 1,000. We're not going to use that one. 51 jobs, 21 jobs. And then you can also run it on some simulators. So let's, I don't know. I guess we'll do this one. Okay, so we'll run it on that one. So the job has been, uh-oh. Let's try that again. There we go. Okay, so it created the job, it compiled it, validated it, and now it has sent it off to the queue to be run on that actual quantum computer. And I think it's going to take a couple of minutes for it to actually make its way to the front of the line and then be run. Oh, okay. When I did this right before class, it took a couple of minutes, but now they say it's going to be done in just a few seconds, so we're good. Let's see, does it tell us when it's done? Oh, we're running it. And we got a result. And the result is, it came up 0. What is this? About 85% of the time, 90% of the time. And it came up a 1 only 10% of the time. So that's quite a bit of different result from our little simulator in which it was almost 50-50. This one is going to be almost 100% of the time. 90% of the time, it came up heads. And we can take this out. Let's see, can I delete that? In which we elect not to flip the coin. I'll go ahead and run that. And hopefully it'll run pretty soon. I don't know if it lets me know when it's done, or if I have to refresh this. Well, I'll come back to that in a few seconds. So you're not just sitting there watching this. So as I said, for a classical bit, you've got only two values, 0 and 1. For a quantum bit, called a qubit, kind of occupies this spectrum from 0 to 1. Oh, we got our results back. Let's see. And the result is the same. About 90% of the time it came up heads, and about 10% of the time it came up tails. So it doesn't matter whether you, as the human, elect to flip the coin or not. The result is still going to be the same. Okay, so since a qubit can represent a spectrum here from 0 to 1, there could be maybe a 25% chance that it's a 0 and a 75% chance it's a 1, or maybe it's 50-50, or maybe it's 90-10, right? So it could be anywhere on that range. And so rather than representing a qubit as a one-dimensional value, it's more convenient to represent it as a two-dimensional value on an axis. So over here, this is the 0 axis, and this is the 1 axis, okay? So if you have your quantum bit over here, that means it is in the 0 state. And if it's up here, it's in the 1 state. So if we kind of use Cartesian coordinates to represent these, this here is at 1, 0, and this one here is at 0, 1. Okay, and the reason why I'm choosing 1 is because we're really on the what's called the unit circle. That's a circle with a radius of 1. All right, so you're kind of following that. So if your qubit is over here, it's in the 0 state, and we can represent it with the xy coordinates 1, 0. And then if it's in the 1 state, we can represent that with 0, 1. And then if it's halfway in between the 0 state and the 1 state, it's sitting here. And the coordinates of this one is 1 over root 2, 1 over root 2. And you get that by looking at the right triangle that would be formed there. 45-degree angle. If the hypotenuse is a 1, then the height is 1 over root 2, and the width is 1 over root 2. And we call this the plus state. So that particular point on the unit circle has a name. It's called plus. Okay, are we good so far? There's also a minus down here. And this would be 1 over root 2, negative 1 over root 2. And that's called minus. So this unit circle represents the probability that the qubit is in either the 0 state or the 1 state. And some of you might be asking, well, that means that some of the probabilities could be negative. You know, and that's true, but really what this unit circle is representing is almost like, well, actually what it's representing is usually the orientation and the spin of the quantum particles being used. And so the spin can be either clockwise or counterclockwise, and then it can either be facing up or left or right or down. There's actually 6 orientations, I believe, for a quantum particle, and then there's 2 spins, which gives you a total of 12 possible orientations for it. And so really, the quantum particle can be on a unit sphere, which is actually why they're showing a sphere here, because there's an x direction, a y direction, and a z direction along with a spin. And so yes, it's possible for it to be in the negative side, because really what you're doing is you're saying the particle is now oriented like this way and it's spinning, you know, counterclockwise or clockwise. And so each one of these operations, these x, y, and z operations, change its orientation by rotating it at 90 degrees along one of the axes. Okay, so if you haven't already, take a linear algebra class, because you'll learn about matrix manipulation, which is really important for quantum computing. With classical bits, all you have to know is about 1 and 0. With quantum bits, you have to know about ones and zeros and probabilities, and two-dimensional representations of positions. And so that's where a matrix can come in handy. And for our purposes, I'm just going to show you how to do the one matrix multiplication that you need to be able to do. So for a classic bit, we've got a fundamental not operation, and if you do a not on a 0, you get a 1, and if you do a not on a 1, you get a 0, right? So think of not as being like a function. You put in a bit, and you get the opposite one out. So under quantum, if I do the x operation on the 0 quantum bit, I should get the 1 quantum bit. And if I do the x operation on the 1 quantum bit, I should get the 0 quantum bit. Right? So basically, if the bit is over here, I'm going to move it over here. And if the bit is here, I'm going to move it down there. Are we good so far? Okay. So we've represented the position of the qubit using the sort of standard XY coordinate pair of numbers, but you can also represent it as a matrix, and in this case it's written vertically. Okay, so 1, 0, written as a Cartesian coordinate, can also be written as 1, 0, written vertically, and then you use the square brackets to say this is a matrix. And 0, 1 is equal to 0, 1. Okay? And the nice thing about these quantum transformations, like the X operation, and we'll find out about the H operation in a moment, is they can also be represented as matrices. So the X's matrix is 0, 1, 1, 0. It's a 2 by 2 matrix. So doing the X operation on the 0 qubit is equal to just swapping in this matrix for X and this matrix for 0. And doing the X operation on the 1 qubit, you do the same thing. You just swap in the matrices. Oh, I had this one wrong here. Okay. So here's how you do matrix multiplication. If I've got a 2 by 2 matrix multiplied by a 1 by 2 matrix, I will get a 1 by 2 matrix. So I'll get a number up here, and I'll get a number down here. And the way you calculate the top number is you do AX plus BY. So you pair up these two and these two, and you add those together. And then the bottom number is CX plus DY. You pair up these two numbers and these two numbers. Okay, so we got our not operation. We got x of the 0 qubit is equal to 0, 1, 1, 0, and then 1, 0. So this is x, and this is the 0 qubit. And then we'll just multiply. 0 times 1 plus 1 times 0 is the top, and then 1 times 1 plus 0 times 0 is the bottom. And this gives us 0 plus 0 and 1 plus 0, which is 0, 1. And that is exactly what we wanted. So we took the x operation, applied it to the 0 qubit, and we got the 1, 1. We got the 0 qubit out. The 1 qubit out. And if you do the same thing for the 1 qubit, then you get 0 times 0 plus 1 times 1 over 1 times 0 plus 0 times 1, which is 0 plus 1 over 0 plus 0, which is 1, 0. And that's what we wanted also. That if we apply the x operation to the 1 qubit, we get the 0, 1 out. Okay, so how can we do this in C? So we need to define something that will represent a qubit. How about a struct?
Yeah.
The struct will hold two numbers. It'll hold a number that represents how far onto the 0 axis we are and how far on the 1 axis we are. And let's make each one of those be a float. And then we'll give it a shorter name as well. So we can just say qubit. So we can do this. Qubit, let's call this Q equals, and then we could do 1, comma 0. We could also do qubit B equals 0, comma 1. So I can very easily assign values to both the 0 and the 1 axis in the particular qubit. I could even do qubit C equals, let's say, 0.5, comma 0.5. I could do something like that, right? Okay, so I can very easily create qubit variables and assign values to them. So I think what I need here is I need like a print qubit. And this will be easy. We'll just print it out as, I guess we'll just print it as a matrix, right? Except we'll do it, we'll just flip it back horizontally. So now I should be able to call print qubit on Q and have it print out its value. Let's go ahead and try that. Okay. I think we're good so far. So now let's make a function called not. So why don't we call it, yeah, we'll just call it not. That should be okay. Or we can call it x. Or we'll just call it x, right? Because that's the name of the operation. So the x operation is going to take a qubit in, and then let's have it not modify that qubit, but actually return a new qubit with the new values. And I'm going to capitalize this x, just so it doesn't look like a variable. Okay, so we're going to make a function here called x. It's going to take a qubit in, and it's going to return a qubit. So rather than modifying the qubit itself, it's going to return a new one. And then this is going to do those matrix operations. So let's make a qubit. Let's call this n. And then we go n dot 0, which is the top number, equals q, oh, what is it? So now we have to look over here, right? So we're going to do 0 times the top number plus 1 times the bottom number. 0 times the top number plus 1 times the bottom number. And then the 1 number is going to be 1 times the 0 number plus 0 times the 1 number. And then we'll just return n. And then down in our main, we'll say print qubit x, and then we'll pass in q. So when we print out the qubit, we start with 1, 0, and after we apply the x operation, we get 0, 1. So what's going to happen if we apply the x operation twice?
You're going to go back to the way that it was.
Yep. So it flips it to a 0, and then flips it back to a 1. Now, let me ask you this. How do you feel about the x operation taking a qubit and returning a new qubit with the values that have been flipped, versus just modifying the qubit you were passed in directly? So the way I've got it written here, it doesn't really model what's actually happening to the qubit inside the computer. Inside the computer, it's actually modifying the qubit itself. It's got one like atom or one photon, and it's changing the state of that photon. In this one here, in this simulator, we're taking a qubit in, and we're generating a new qubit, and that's what the return value is. Mathematically, it all works out the same way. But some people feel a little funny about this because this is not what's like really happening. And so one of the problems here is that this x operation gets a copy of the qubit that's being passed in. So it actually doesn't even get the original qubit. It gets a copy of it, and then it does the math, and then it returns a new one. So really what's happening is you start with an original qubit, and then after applying the x operation, 2 new qubits have been created. The original one got thrown away, and then the intermediate one got thrown away. So we could fix this by not passing in a copy of a qubit, but getting a qubit pointer. And then we can modify the qubit itself. So in this case, X is going to be a void operation. It's not going to return anything. It's just going to modify the qubit we were passed in. So we don't have to create a new one. We can just say Q pointer 0. And Q pointer 1. And then there's nothing to return. Okay, so now we're modifying the qubit itself. And then here, we can't just apply the X operation and then print it out. We actually need to do the X operation on the qubit and then just print out the value of Q. And then we can do the X operation on the qubit again and then just print out Q. Oh, we have to print. We have to pass in. We have to pass in the address of this because we have to pass in the pointer to it. There we go. Oops. What did I do wrong here? Line 19. Oh, I forgot one of these arrows. There, I think I fixed all the errors. There we go. Uh-oh, something went wrong. We got a 0, 0 out of here. Oh, we got a 0, 0 because in assigning it right back to the same qubit, we actually zeroed out one of the values. So, you know, it's almost like we need to make a qubit. This is seeming like it's actually a bigger, more hassle than originally it was. There we go. That's better. Okay, so I had to make a temporary qubit and then assign the 0 and 1 values to that qubit and then put them back into the qubit that I'm modifying. Okay, so the Hadamard operation takes a qubit that's in the 0 state and puts it into the plus state. So it takes one that's here and it puts it into a superposition so that it's neither a 0 nor a 1. So that's what the H operation does. It takes a qubit that's here and it moves it here. So if I take the 0 qubit and apply the H operation, I should get the plus qubit out of that. So the H operation can also be represented as a matrix, and its matrix is 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. So it's also a 2 by 2 matrix with all 1 over root 2's except for a negative down in the lower right-hand corner. So if I do H on the 0 qubit, that's the same thing as doing the H matrix. Applied to the 0 qubit. This is H of 0. Okay, and then we'll just do the matrix multiplication. So first is that pair of numbers, 1 over root 2 times 1 plus 1 over root 2 times 0. And on the bottom, we've got 1 over root 2 times 1 plus, whoops, minus, this is a negative here, minus 1 over root 2 times 0. Okay, and so we get 1 over root 2 plus 0 on the top and 1 over root 2 minus 0 on the bottom, and that is 1 over root 2, 1 over root 2. Woo, that's exactly what we wanted. Okay, so we can do that over here. Let's make an H. We take in a qubit pointer. We'll make a temporary one. And you know what I'm going to do is I am going to make a constant called like R2 or something like that, because we do these 1 over root 2's all over the place, and I don't want to type that in over and over and over again. So let's just go like const float. I'll call it R2 equals 1 divided by the square root of 2, 2.0. And in order to do that, I'll have to include math.h, because that's where the square root function is kept. Okay, so we have so R2 times Q pointer 0 plus R2 times Q pointer 1, and temp.1 is equal to R2 times Q pointer 0 minus R2 times Q pointer 1. And then we'll put those values back into Q. Okay, so let's take Q and apply the H operation to it, and then print it out. Let's pass in a pointer to Q. Oh, and I need to link in the math library. No. Initializer element is not a compile time constant. Oh. You know what I'm going to do? Was it 1.414? Can I just copy that?
141421.
1.41421. Can I go a little bit further? 35624.
35624.
35624. Whoops. 35624. that I think should be more digits than a float can hold. There we go. Now I don't need the math library. Okay, so we started out with our 0 qubit, and we ended up with the qubit being in a superposition. So it's halfway in between the 0 and the 1, which is good. Okay, so what do you think is going to happen if we apply the H operation to that qubit now?
It's going to go to the negative position.
All right, let's see. Well, that didn't work out the way I wanted. Did I do something wrong with here? Let's see. Q0 to Q1.
Mine went back to, it went from 1 0 to 0 1.
Okay, R2 times Q pointer 0. Plus R2 times Q pointer 1. Good. R2 times Q pointer 0 minus R2 times Q pointer 1. Q pointer 0 equals temp 0. Q pointer 1 equals temp 1. So you got a different number than I did?
Yeah, so, well, I did it twice. Where did you run it? Yeah, I did the same thing. But I started with 0 1. So I got the first one
Oh, I see.
gave me 1 0, and then it gave me
Yeah.
0.7, negative 0.7, and then it gave me 0 1.
Yeah, so
So if I switch
I
that
see what
to
the problem is.
Q-
I see what the problem is. My R2 is not 1 divided by this. It's just 1.414. It should be 1 divided by that. Point 707,106. Seven eight one two. That's my problem. There we go. That's what I wanted. Okay, so if I take the 0 qubit and I apply the H operation, it goes into superposition. And then if I apply the H operation to that one, it goes back to the 0 qubit. Okay, so if I apply the H operation, it goes here. And if I apply the H operation to that one, it goes back. So we can kind of make like this state diagram that says if I start here and I apply the H operation, I go there. And if I start there and I apply the H operation, I go back to 0. And if I apply the X operation to the 0, I go to the 1. And if I apply the X operation to that one, I go back to the 0. And then you did one where you said, I'm going to start out in the 1 position and then apply the H operation.
Yep.
Let's call this Q1 is equal to 0, 1, right? So if you apply it to the 1 qubit, you get the negative qubit.
We're still looking at your white screen,
Oh, sorry.
or your whiteboard.
So I just did this right here.
Mm-hmm.
And then I got this.
Yeah, it
result.
goes down and then it comes back. So how do you get it from superposition to the upper one? To go from 0 to superposition to 1?
So you want to go from here to here?
Yeah.
Oh, you got to go here and then here.
Ah, I see.
You got to do H and then X.
Got to follow the diagram.
So you discovered that there's this new position down here. And that if I apply the H operation, was that the H? Yeah.
Yeah.
From here, I go there. And then what do you think will happen if I apply the H operation to this one?
It goes back.
It goes back to that one, right?
Yep.
What do you think is going to happen if I apply the X operation to this one? Oh, what do you think is going to happen if I apply the X operation to this one? The plus.
It's going to go to the negative. So it'll be in the superposition of the negative side. That's a good, let's find out.
Okay, so let me erase this stuff here. So I've got my qubit that starts out in the 0 position. Let's call this Q0. Let's just call it Q. I'm going to apply the
there.
Hadamard, and then I'm going to apply the X to it.
It doesn't move.
No, it doesn't move. What do you think about that?
I think it's a knot, so it should do something.
But so
it makes sense though.
But when you think about it, it makes sense, right? You've moved the qubit into this superposition where it's in between a 0 and a 1, and then you flip it, and it's still in between a 0 and a 1.
Yeah, it's still in the middle.
It's still in the middle,
regardless.
right?
That makes sense. Yeah.
Yeah.
That's neat.
And so that's why that computer game was able to work.
Because it can be either.
It started out here with it in heads, which is the 0. It did a Hadamard operation, which put it in superposition. And then you can flip that coin as many times as you want, and it will just sit there. And then the computer finally brings it back out of superposition and puts it right back into heads.
It is cheating.
Yeah, it is cheating a little bit. It's cheating a little bit there. Yeah, so we can do this X operation as much times as we want, and it won't change its value until we finally put it back. Right? So we started out in the 0 position, and we ended up back in the 0 position. What happens if we, let's call this Q1 equals, yeah, let's start this out in 0, 1. We'll do the H operation to it. And then we'll do the NOT operation to it. Where did we end up?
Negative. Lower half.
So where is that?
The pipe 0
Is it here?
greater sign. Yep.
Let's see, according to this, it ended up at negative 1 over root 2, positive 1 over root 2.
Oh no, that would be the third,
So negative,
second quadrant.
negative 1 over root 2, positive 1 over root 2.
Yeah, that'd be the second quadrant. It
So
can't
here.
go over there though. Can
So-
it go over there?
Sure. There's actually,
Well, I guess if
There's
you're on a
actually-
unit circle, it can go
yeah,
anywhere,
there's
right?
8 positions. There's 8, really like fundamental positions here. So the X operation from here takes you over here.
Wow.
So with combinations of these X's and H's, you can move that qubit all around that unit circle into different places. And depending upon what you want your calculation to do, you use combinations of those things. So a typical quantum program, has combinations of H's and these things here are called, whoops, you can't see what I'm doing. These are called C0 operations. This is a conditional not. So it'll flip one qubit depending upon the state of another qubit. It's very similar to the exclusive OR operation in classical computing, in which if you look at the truth table for exclusive OR, you can see that it actually flips bits. So if the first bit is a 1, it'll flip the second one. The exclusive OR truth table. So this is the truth table for exclusive OR. And so if the first bit is a 0, it'll flip the second bit. Oh, sorry, if the first bit is a 1, it'll flip the second bit. So here, these are zeros, and so these two bits are the same. And here, these are 1s, and so these bits are flipped. So you can think of the exclusive OR operation as flipping one of the bits, depending upon the state of the other bit. So in quantum computing, this is two entangled qubits. The state of one affects the other.
Oh man, making my brain hurt. That's crazy.
So in a quantum computer, now this is actually one thing that I had to get my head around is the programs we're running for a quantum computer aren't modeling the way quantum things work, right? But it's flipped around from that. It's we are designing a computer that behaves the way we want it to behave. Okay, so just like in classical computing, we defined an operation called exclusive OR, and this is the truth table for the way it works. And then we designed electronic circuits to make computers do that.
Right.
As opposed to trying to explore the fundamental behavior of electrons in an electronic circuit, we are making electronic circuits behave a certain way.
Right, that makes sense. We're saying this is the fundamentals of it, so let's build it around that rather than let's change the laws of physics.
Yeah, so the H gate is we want to design a quantum circuit that makes the quantum particle behave that way. It takes it out of the 0 state and moves it into superposition state. And so I don't know how the mechanics of how the computer actually does that, but that's what that H operation does. Is it takes it out of the 0 state, or in this case the 1 state because we just flipped it here, and moves it into superposition. Now this is interesting. There's two H's in a row, and as we know that what does that do? It let's see, according to our diagram, two H's in a row.
Just takes it back. It moves it to superposition and then brings it back.
So it starts out at 0, it does the X, so it moves it over here, and then it does an H, which moves it there, and then it does an H again, which moves it right back there. Not sure why, but it has to do that. And then there's the C0, here where it says, depending upon this one here, and this one here has been put in superposition, so half the time it'll flip this one, and half the time it won't flip it. Same thing here. This qubit is in superposition, so half the time it'll flip this one, and half the time it won't. So Grover's algorithm is essentially what we would call linear search in the classical sense. You've got an unordered array of values, and you want to find the one value that meets the certain criteria. You know, like the biggest or the smallest, or whatever the criteria you want to use is. You do a linear search on an unordered array, and you find the one element that meets the criteria. Grover's algorithm is the quantum equivalent to that. You've got an array of qubits, and you want to find the one qubit that exhibits the property that you want. And this algorithm will do it, but it will do it in a way that it requires only the square root of the number of qubits operations to do. And it looks longer than it is here. And that's because we're operating on a fairly small number of qubits. If we had a larger number of qubits, it wouldn't it would still be approximately the same length, but we'd be able to scale it out to more qubits. And so you can use this thing to do like which qubit represents the array element with the biggest value. And instead of searching linearly through that array and finding the one biggest one, you only have to search through a square root of the number of qubits, and you'll know the answer.
Mm-hmm.
So it can search an unordered array faster than a classical computer can. Not instantaneously fast, but faster.
Probably faster than a classical can when it's ordered.
Classical
Or
can, when it's
root,
ordered,
right?
can do it in log n time, which I think is faster than square root.
Yeah, you're right. Log n would be a little bit quicker.
But you'd have to sort it first,
Yeah.
and that would take n log n time. So really, to search for, well, actually, if you're searching for the biggest element, all you have to do is sort it, and then the biggest element's at the end.
Oh, you're right. Yeah, that's true, huh?
But still, the sorting takes n log n time. So
Yeah.
that is slower than square root of n. So if quantum computers really do, take off like they're expected to in the next 20 or 30 years, you could potentially do searches really fast. You wouldn't have to sort them ahead of time. You could do things like factor numbers quickly.
Oh, yeah. All kinds of stuff. That's so neat.
So that's my little introduction to quantum computing. And essentially, we just wrote a little quantum simulator, kind of. Although what we can't simulate with ours is these things like these entangled bits. We don't have any way of simulating that. What we would have to do, I think, to make a proper quantum simulator is we can't just simply put these qubits into 1 over root 2, 1 over root 2. We basically have to add a little like randomness to it so that half the time it's 0, 1 and half the time it's 1, 0. And then we just sample it, let's say 1,000 times. And if we did that, we would get a 50-50 chance of it being one or the other. So we would have to not just represent it as static numbers, but actually as random bits that are flipping between zeros and ones randomly. So every time we look at it, it's either a 1, 0 or a 0, 1.
And take the average of that.
And take the average, yeah. And the average should come out to be 1 over root 2.
Yeah. Yeah.
Well, average would actually be 50-50. But the way you compute an average of something on a unit circle is you apply the Pythagorean theorem to it.
Yeah.
You square both sides, and then you add them together, and that's where you get your 50% from. Oh, you can also see over here that you can, in addition to dragging and dropping the various blocks into position here, you can actually write it in Python. So there's a Python library called QISKit that you can get that will allow you to write what looks like classical computers, but it runs a quantum simulator. So if you can't get access to the quantum computer that you want on IBM, or you have to wait a long time, at least you could run it on a simulator. And depending on the algorithm, it might take longer to run because it has to run it 1,000 times, right? And essentially each qubit can represent any number of an infinite number of possibilities. So potentially you've got exponential time to run that program.
Oh, yeah.
Because essentially, to really simulate it, it has to try all possibilities. There's a possibility that this one is a 0, and this one's a 0, and this one's a 0, or this one's a 0, this one's a 0, and this one's a 1, or this one's a 0, this one's a 1, this is a 0. So it has to try all, in this case, 8 possibilities in order to arrive at the answer. Nevertheless, it's a good first step towards adapting a traditional programming language to work on a quantum computer. Okay, I think that's it for today.
That was fun. I love this stuff. I don't understand, like, I mean, I get what we talked about, but boy, it's complicated. Getting into like the idea of how it actually works.
Yeah. I
Mind-boggling.
mean, I assume that in 5 or 10 years, we won't have to worry about that.
Yeah.
We'll have a programming language that works with quantum computers, and you don't have to know how the quantum computer actually works. Just like today, we got programming languages that let us write programs, and we don't have to know how electrons actually flow through the silicon.
Yeah.
We just assume someone's taking care of that, it works reliably, and
Yep.
we can write programs. And so, again, in 5 or 10 years, we'll be able to write quantum programs, and it just works. And then when we'll actually have those things on our desks, I'm not sure.
Yeah. Who knows? That's neat though. Yeah. I remember you telling us, for anybody that didn't see it, when you look at the picture of the quantum computer, it's just that little tiny
Oh, yeah.
square in the middle, and the rest of it is all the cooling that cools. So the whole giant thing is cooling with just the little tiny square in the middle.
Yeah, all this stuff is just measurement and cooling, and the actual quantum chip is that little one right there.
It's so crazy.
And I just, it's something that flashes in the back of my memory, in the back of my mind, that those things, those chips are actually not that complicated. So I saw someone that said, like, he was just holding on his finger, right? It's just a little chip that just happens to trap like a photon inside of it when attached to the correct cooling stuff. But apparently, I guess the implication was, you can buy somehow the cast-off chips that didn't work fairly inexpensively.
Wow. That would be neat.
Yeah. Here's
Put it
a
in
quantum
like a
computer
shadow
that
box and put it on the
doesn't
wall.
work, right? But
Yeah. I wonder how many of those they make that
I
don't
have
work.
no idea.
I guess if you can buy them for not very expensive, I would guess they probably make a bunch.
Yeah, I would guess that, this is not the complicated part. All this is the complicated part. Right?
Right. Yeah, all the measuring.
And the cooling and the, yeah.
Yeah, boy, getting it close to absolute zero, that is cold.
I had this thought the other day, and this is, I have no idea whether this is anywhere close to reality, but in today's classical computers, so you might have heard about this thing called Moore's Law, which
I thought about the same thing you're
it's
thinking
more or
of.
less true. It basically says the original Moore's Law was the number of transistors that they can pack into a given square unit of area has been roughly doubling every, year and a half, 2 years or so.
18 months. It was 2 years first, and then they changed it to 18 months.
But they quickly kind of, not just recently, like within the past 10 or 15 years, kind of hit a limit where you just can't get them any closer without them like interfering with each other. You got these quantum effects, right? Or one transistor affects another one right next to it, even though they're not physically connected due to capacitance and stuff like that. And so one of the ways that they've managed to still achieve this Moore's Law ramp up is not in the number of transistors per square inch or so. It's in just the speed of computers, how fast they can do calculations. And again, we've kind of hit a plateau where we've basically maxed out at about 3 gigahertz or so. It's very, very rare to find a computer that's a whole lot faster than that. It's certainly not doubling. It's not going up to 8, 12, 20 gigahertz. It's kind of stopping. And so, of course, you've seen the way they've addressed that is just adding more cores.
Yeah.
Right? So you still have a speed of about 3 gigahertz, but now you've got 6 cores and 8 cores. So the number of cores is now roughly doubling every 18 months or so. And another way that they've addressed some of these speed issues is by having the processor do more work per cycle. And one of the places where it does more work, well, first of all, you've probably heard about hyperthreading, where the processor will look at the instructions coming in and determine if a pair of instructions that are next to each other can be run independently or if they depend on each other. So for example, if I have like add 5 to register 6 and then add 10 to register 6, well, I can't run those at the same time because the result of one depends upon, the second instruction depends on the first instruction, right? So I can't run those independently. But if I had something like add 3 to register 5 and then add 6 to register 8, well, those can be run independently of each other. So it can then run those two instructions in parallel on two separate, what are called hyperthreads. And so the processor just analyzes your program as it's running, and it sees if there's instructions that can be run like that. And when it sees them, it just runs them in parallel. And the compiler can also help out by making sure that instructions that can be run independently end up close to each other in the program, so the processor can see that they are consecutive instructions and can be run independently. So the compiler can actually reorganize your code to take advantage of the fact that you might run on a hyperthreading processor, and if it does, it'll run faster. If it separates those instructions by too much, then the processor won't see it and it won't run them separately. Another thing that's being done is with what's called branch prediction. When it comes to an if, the processor can try, actually the compiler will try to predict whether that if is true more often or false more often. You can actually look at other parts of your program and say like, well, if you're using integers and it looks like the integers range from 1 to 100, and it looks like most of the time they're going to be towards the upper end of that, then maybe it's going to be true more often, right? And then it can reorganize the block of code that gets it got executed for the true or false values, either one or the other first. Okay, so if it's going to be true more often, it might put that one at the top, and then the processor just simply falls through to the next instruction, rather than having to jump over the block and then go to the other one. Does that make sense? Right, so reorganizes the if, the true and false blocks, depending upon which one it thinks is going to be true or false more often.
And the Tiger Lake processor remembers that, and it continues to do that over and over.
Yeah, and so kind of related to that is now what processors are doing is when they come to a branch, they actually fetch both instructions from the true block and the false block simultaneously. Remember, there's a pipeline that goes fetch instruction, decode instruction, execute instruction, and then store the result. And there's that, and some of the pipelines are even longer with those steps broken down into smaller steps. Okay, so you've got fetch, decode, execute, store. Those are the four basic operations. Well, if your pipeline could potentially go in parallel, then you could fetch the instructions from both the true and the false blocks, decode them both, execute them both, okay? By the time you've got to that state, you've now figured out whether the original branch was true or false. Because it's just one step ahead of you in the pipeline, right? So it's one step ahead of you. So now you've figured out, by the time you got to executing the two instructions from the true and the false value, you've now figured out for sure whether that branch was true or false. And so you can just skip the store step for the one that was false.
Yeah. Huh.
So you execute both of them, but you throw away the results from one of them once you've figured out whether that branch was true or false. And that's how the current processors are working, is in order to do branches faster, they start executing both branches, and then they just simply halt the execution of the one that ends up being false.
Wow.
Kind of cool, huh?
That's super cool, yeah.
And unfortunately, some hackers have tried to figure out how to take advantage of this, because it means that now both instructions are in the processor at the same time, which means it's doing memory fetches at the same time, and so they figured out how to access the memory of the false branch, even though it won't get executed, but now they can kind of look at the values in there. That's beside the point. Well, my point was, and the thing I was thinking about the other day, and I have no idea whether this is true or not, is this is almost like a quantum thing, right?
happening at the same time.
No,
yeah.
the result of the branch is not known until we measure it.
Yeah.
So the result of the branch is kind of like in a superposition. We don't know whether it's true. We don't know whether it's false. We won't know until later whether it's true or false. So, and again, this is pure speculation on my part. What if instead of having full quantum computers on our desktops, what if we're able to embed little like bits of a quantum computer in our classical computers to put like a branch instruction into superposition and then measure it, and then measure it later.
Yeah.
Right? Just take advantage of the fact that we don't know the result of that comparison until we measure it.
Mm-hmm.
You know, so instead of going wholesale, like here's a whole quantum computer, a whole general purpose quantum computer, why can't we just take one little aspect of it, the superposition aspect of it, and stick that into a regular computer? And maybe make
Wow.
our comparisons go a little faster. Take advantage of the fact that we've got one bit in there that can go both ways. I don't know. I was just thinking about that. Like a way to start like integrating quantum computing into classical computing.
That's not what I was thinking. That's amazing.
Anyway, oh, somebody on YouTube says, I have a question. We'll find out in 20 seconds what it was.
I was thinking along the lines that if it's every 18 months that we double the capacity with classical computers, when we get into quantum computers as a norm, is it going to be every 6 months because it's going to go so much faster and be so much quicker?
I don't know. I mean, some
And then
people have
it's just
said
going to
like
skyrocket.
this is pure theory here, but someone has said once quantum computers reach 53 qubits, we've effectively made classical computers obsolete. And the reason for that is that, well, a classical bit can either store a 0 or 1. So one bit can store can store just one value, either a 0 or a 1. 2 bits can store one of 4 values, 0, 0, 0, 1, 1, 0, 1, 1, but only one set of those at a given time. 3 classical bits can store one of 8 values.
Right.
Okay, but a qubit can store an infinite number of values between 0 and 1. So it can kind of store both the 0 and the 1 simultaneously. And 2 qubits can store 4 values simultaneously. And 3 qubits can store 8 values simultaneously.
So
53 qubits.
Be what, 53 to the
2 to the 53rd.
That's a big number. 9 times 10 to the 15th.
Yeah, 9 times 10 to the 15th. They say that's more classical bits than the whole world possesses.
Wow. So if you linked everything.
Yeah, if you took every computer and
that's
somehow
wild.
linked them all together, it would have roughly, that number of classical bits. And so they say once you've reached 53 qubits, you've outpaced the computational power of every computer on the planet.
Wow.
And we'll certainly need more bits than that to do the kind of computations we want to do.
Yeah.
Like if you want to factor, factor RSA keys, you need like 2,000 qubits to do that. Oh, let's see. The question was, how can I become a developer for the Linux kernel, and what's the best book for that? I actually don't know the answer to that. I have not actually done any kernel development myself. So I'm afraid that is not something that I could answer satisfactorily. But I would suggest get yourself onto one of the Linux kernel mailing lists, email lists, or discussion boards, and start following along. And participate in those discussions if you can. because that's where you'll probably do a lot of learning about that Linux kernel. Well, I think we've chatted enough. We've reached the end of our
Very
week.
fun. Yeah.
So really, honestly, within the next day or so, I should have that calendar up.
Okay.
And actually, I wonder, if you go onto our website, our Canvas website, do you see a link there that says Confer Zoom? I don't know if that's visible yet. If you go onto ours, do you see one that says Confer Zoom?
The right window here open.
Edward asks, Moore's law has pretty much slowed down, hasn't it? That's what I was talking about, is that we've kind of plateaued as far as the number of transistors per square inch, and we plateaued on the speed, and so we're making chips bigger. We are actually still packing more transistors in, so that's definitely happening, but not at the rate it used to be. But we're just adding the number of cores, getting the computer to do more work per cycle. So do you see that?
Yes.
And so if you flip over to next week, does it show a calendar? I don't know what your
This
view
week
looks
starts on the 6th.
like. Yeah.
Well, you can do so. There's, let's see, event calendar.
There should be a week view you can flip to.
Oh, right there. Next week. There's a view, but there's nothing in it. Look at appointment booking. Yeah, there's appointment booking also, but there's still nothing in it.
Nothing in it? All
Yeah,
right.
you have no upcoming appointments to show.
All right. I have some work to do then to figure out how to get that to show. So again, look for that. I'll post an
Confer Zoom.
announcement. Yeah, Confer Zoom, which should do appointment booking.
Yeah,
For
so that's what Gita Furoi, that's what she uses.
Uh-huh.
So if you want to ask her, I'm sure she could tell you what she
Okay.
does. That's what she uses for all of her stuff. That way you're not trying to
Okay.
sit down and figure it out.
Okay, I'll ask her. So again, there's that. There's finding a time slot that works for you, and then there's filling out that end of semester reflection survey.
Cool.
All right.
Sounds good. Well, that was fun. Thank you. I very much enjoy those. A blast.
Yeah, and I'm learning more. I'm taking, or not taking, I'm watching a lecture series from, is it Harvard or MIT about, it's MIT I think, about quantum physics. I don't follow a whole lot of it because, I mean, the first two lectures were really interesting because the instructor made analogies with like something from your own experience.
Mm-hmm.
But then once they got into like wave functions and stuff like that, I went, I don't understand this anymore. I did not take the prerequisites for the class.
Yeah.
But the first two
That's
lectures
neat,
were
though.
interesting.
Yeah, that's cool. Yeah, that'll be fun to, eventually it's going to be something that's going to be taught.
Yeah, definitely.
That'll be neat to take those classes. Cool. Well,
Okay.
thank you.
Yep.
That was fun. I
All right.
appreciate it.
We will meet on Tuesday. I do have
Okay.
like a 1 hour Zoom session for us to do there where we can just wrap up the whole semester.
Okay.
And then otherwise next week it's all just those little meetings and figuring out your grades.
Sounds good.
All
Cool.
right.
Well, then I will see you Tuesday. Have a good weekend.
All right. You too.
Thanks.
Work on your
Bye-bye.
assignments. Get them caught up.
Yeah, I will. I just got to do the networking one and I'll be done.
Ah, jeez. Yeah, I'm working on I'm the big one for that one. Slowly but surely. Slowly but surely. I don't know if I'll get them all done, but I'm trying.
All right.
All righty. I
See you
will
later.
see you Tuesday. Bye-bye.
Bye-bye. Let's see. Socket is written in the C language. Yeah, the original Socket libraries certainly were. Only because Socket goes kind of like with Unix systems, and Unix was written in C. Other operating systems for a while had their own versions of the TCP/IP stack. Like Windows had one called WinSock, kind of like WindSock, and Mac had one called Mac TCP, and those were not based upon, well, maybe WinSock was based on a socket library, but Mac TCP certainly wasn't. And then when both those operating systems became more Unix or more Linux-like, then I think they switched over to just using the socket libraries that are maintained by the Linux and Unix people, because they work, they're reliable, and they've been around a long time, and they're stable. So I think I'm going to wrap it up here. I've got work to do. It's almost the end of the semester, so I got work to do. And I will see you all next week. So we will have another meeting on Monday, and on Tuesday we're just wrapping up the semester and kind of going over everything that happened during the semester. And then it will be on to our winter break, which will take us through mid-January. Maybe there'll be some opportunities for me to do some live streaming over the break, but we'll see how that goes, because sometimes the breaks tend to be kind of busy with family stuff and holiday stuff. If I do some stuff, it'll be based upon some of the projects I've been working on with my old, where is it? This is all backwards, because my old vintage computers. Here's one here, and there's one over here. I'm working on some network stuff to get some of these old vintage computers talking to the modern internet, which didn't exist back when they were invented. And so getting them to do somewhat similar to modern networking protocols is going to be challenging. But that's something that I've been wanting to do for a while. So that's something I may be working on. Okay. Yes, have a great week. I'll see you all next week. And I hope you have a good rest of the day or good evening, depending upon where you are. And thanks for tuning in. I'll see you all later. Bye-bye.